Okay, welcome back. We're getting started. We are officially in weekend session number 2 of Software Engineering 1. And last time, if you missed the class meeting last time, go online, take a look at the YouTube videos. You'll see everything you missed. What we did was we went over the syllabus, the course notes, lectures 1 through 4, and we covered the requirement specification document. So this weekend, we are covering the analysis, the design, which are 2 separate deliverables, the prototyping. In fact, we're kind of finishing up, essentially, everything you need to do for the project. Later on in the afternoon, I'll talk about the midterm exam. It's a take-home exam. And then we'll kind of, towards the end of the course today, the meeting today, I'll talk about the final exam, which is in July something. But I'll get the date for you by then. So what you're looking at on the screen right now is page 46 of the course notes. It is your next deliverable. So if you're following along with the course and you attended the last meeting, you probably, hopefully, developed a team already. By that meaning, picked some members, picked a topic, and maybe you already did the requirement specification document. I seriously doubt anyone has done anything, but that's me being pessimistic. You could have, and you should have already.
Well, I have a bunch of them.
Yeah. You have a bunch of what?
I have a bunch of these documents.
Okay, no, that's good. That's good. It depends on the level of, what you've done in the past and what your exposure to software engineering is. And for those of you who are sitting here going, oh, we're supposed to pick teams, we're supposed to do a project, oh my god, what are we supposed to do for this? You can work solo. You can work as a team of 1, and you can invite some invisible friends to join you, and you can have a huge team, and you could be the captain of it, and pick and rule the team. Pick your own topic. I don't assign the topics, so pick a topic of a software engineering, software development, something software is the key component. I have had students try to develop hardware problems, or solve hardware problems and develop hardware stuff. It's like software engineering course, so maybe pick a focus on a software. And then if you look at the syllabus, you'll see the breakdown of the course. About 55% of it is on this project. So there are no assignments for the course. You're putting together a requirement specification. You're putting together what you're looking at right now, which is the analysis document. You're putting together a design document, a prototype. And I'm going to talk about those 3 items today. That's the focus of today in terms of what we're doing. And then you don't have to do a presentation. The syllabus talks about a class presentation. You do not have to do it. There is no presentation. It's just one of the things would be kind of infeasible with the sporadic attendance that I've got in this course. So, all right. So let's talk about the analysis specification for a second. Analysis document specification. And as I mentioned before, in the real world, this document does not exist. It is fiction. It's made up. But what this really is the rough draft of your design document. So when I say analysis, to think about, well, we're starting the design is what we're doing. But in terms of your deliverable, what you're going to need to do, again, is start out with section 1 with an introduction. Each one of these documents is self-contained. You can pick it up and read it without reading any of the other documents, which is what I meant by self-contained. So what we're looking at then is providing some overview, some introduction to your project. Now this is a XYZ program of the flying birds or something, and so you're going to introduce, provide a little description so the reader knows what you're talking about. What we know is what's the topic of this particular project, and this is all included in the introduction. And so you have the specific project objectives. What is this project going to accomplish? Overall requirements description. Maybe some project constraints, assumptions, and things. If you don't have the information, don't put it in there. These are some suggested categories of some areas where you can introduce or provide an overview for your topic. And then we go into section number 2 called functional requirements. And I talked about requirements last time, functional, non-functional. And what we're doing is we're building a design based on the functional requirements. It's not a bad focus because what it is we're doing is we're building the functionality, designing it, building it, implementing it. And for your case, you're not really implementing, you're creating a prototype instead. But we have to understand what it is we're building, and in terms of the analysis that we're performing, we're diagramming. So when I say analysis, also I mean diagramming, picturing, focusing on it, understanding what it is we're building, which is how you lead into a good design normally. So what we're going to talk about today is lectures 5 and 6. Well, more than that, but we're going to start out before lunch. We're doing 5 and 6. And the focus is on these two types of diagramming approaches, entity relationship diagramming and data flow diagramming, which are two different models. I'm going to zip through a lot of material, which means you have a lot of reading to do. This document is 113 pages. In here you'll see a lot of stuff on entity relationship, you'll see a lot of stuff on data flow, you'll see a lot of stuff on UML. I'm going to cover a little bit of UML today as well, but this is not a UML design course. You could take an entire course on UML and still not see everything. So what do you need to do here? You need to create an entity relationship diagram. You'll need to create a data flow diagram. And this document can be nothing more than a Word file that you've cut and pasted your diagrams and you put them in there. And in terms of diagramming tools, as you'll see, the diagrams themselves are not very complicated. The symbol sets are very, like a rectangle, a diamond-shaped symbol, a line. So you can use anything you want. There's no required software for this course, but lots of students like Microsoft Visio. If you have it, great. If not, don't buy it for this course. You could use SmartDraw, another program out there. If it puts a little watermark on there or something, or unregistered user, that's fine. It's not a professional course. This is a student assignment. I don't care if there's a little watermark on your picture. Or if you want to use Microsoft Paint, do it the whole manual way with the mouse, draw some boxes and stuff. That works as well. You're not graded on your artistic abilities, and as you'll see, you don't really need any. So use the diagramming tool of your choice in terms of all of the diagrams.
60-day trial period for Visio. They give a 60-day trial period for Visio. So.
Oh, they do?
Yeah, they do.
Wow, 60 days?
60 days. You just need a Hotmail ID for that.
Actually, yeah, they do a 60-day trial for Microsoft Office, I think, as well, when you buy a new computer.
I think that should be.
Also, you might want to look into DreamSpark, but we're working on it right now, getting a license or getting. It's a Microsoft program. You might hear about it in the future. www.dreamspark.com. You need to verify yourself as a student, however. So if you're a student at another university, if you're a student somewhere, you have a student ID, you can verify yourself as being a student. What they do is they look at your email address, and they make sure that the school itself is registered, which is what IT is trying to do right now. So we're not registered yet, so you're not going to be able to download anything. But in the future, probably within, I don't know, maybe a couple months. I'm not sure how long it takes. We just started the process. And then students will be able to download software for educational purposes, but you get the full version, full version of Microsoft Visual Studio.net, full version of everything, instead of the student versions. But it's for educational use, to teach students how to program in .NET and stuff. But there's Microsoft Visio out there as well. So, but don't expect to get authorized unless you have affiliation with another school that is affiliated already. But we're in the application process. Hopefully that'll work out pretty soon for the next term, at least for fall. So, okay, so I'm sorry.
355 ITU11.
Yes, the code, the internet code. It is supposed to be 355 ITU. Does that say 11?
Yeah, it's 1-1.
Okay. Is it working for you?
Yeah.
Yes. Is it working? Apparently, it's not working for you. There might be someone here from the media group that might be able to help you as well. If you go out the door and make a right, there's like a little room. Usually the door's open where people are sitting around. Actually, the TA can perhaps provide some assistance. Okay, so for the analysis document, you'll have to create an entity relationship diagram. You'll have to create a data flow diagram. And you'll have to do some process descriptions. And these process descriptions work along with, and I'll be talking about this today. This is the lecture material. I'll be talking about it. And they work with the data flow diagram. It's the data processing that's going on. And then we'll have some design specifications in terms of an architectural diagram. You might have some performance reliability requirements. You might not. You might have a component or a deployment.
The performance and reliability are non-functional.
Yeah, they could be functional. You missed the discussion last time in terms of what's functional, what's non-functional. As a particular example, let's say you're building a heart monitor and you have some software that's running on the component to control it. It would definitely be functional requirement for it to be 99.9% accurate, perhaps.
Yeah, I think it's,
Or very close. Maybe 100% would be most desirable, I would think, if it's a heart monitor. However, if you're building an air temperature controller and the temperature is 68 degrees instead of 70, it's slightly off, but it's not quite as accurate, maybe it's non-functional. I don't know.
yeah,
So.
that's true.
So it depends on the application that you're building in terms of what you're going to specify as functional or non-functional. That I believe is lecture 2 or 3, and you'll see it if you look at last meeting's videos. You'll see the whole discussion on that. All right, so let's see what these diagrams look like in terms of how you're going to do your analysis and how you're going to compose the items. So we'll start with the concept of entity relationship modeling. So what we're looking is a very simple approach. And if you've taken my database class, you've seen some of this material already related to database design. Believe it or not, entity relationship modeling is often used a lot with creating databases and designing the system, the schematic for the database. And in terms of the tables, the relationships between the tables, in terms of their keys, primary keys, foreign keys, referential integrity, things of that nature, all concepts that come out of entity relationship diagramming. You would think that the data flow diagram, because it has the word data in the description, that data flow would be describing the data components, but it doesn't. It describes the processing. And entity relationship is the one that describes the data. It's in the data component of the system. So the reasoning isn't quite as it isn't quite as obvious as most people would kind of think. In terms of entity relationship modeling, what we're looking at is basically a technique for carrying out the conceptual and logical design of the system in terms of its components. The logical concept is all primarily data related. You think about it. All information systems produce data, and they all have a process to do it. And so in the structured analysis and design approach, we have two models, one for the processing, one for the data. This is a review from last time. I covered this concept last meeting. In UML, they put them together. UML stands for Unified Modeling Language. It's the object-oriented approach. So entity relationship diagramming, data flow diagramming come from structured analysis and design, which is the traditional way of building software. And along came object-oriented design. Didn't replace structured design. Can't. It's not as rich in terms of its functionality, but it's really good for modeling object-oriented programs that are going to be written in an object-oriented language. So unless you've already decided you're not going to build it, you're not going to consider any other language outside of object orientation, then if that's the case, you're going to go as a total object-oriented design approach, analysis and design. If not, if you want to have flexibility, then you're going to do some structured analysis, and when you do it, you're going to do an entity relationship and a data flow diagram. So you have two diagrams, essentially, that end up being the de facto standard in terms of the starting point for your analysis. So widely accepted data modeling approach. So it's a data modeling approach. 3 basic notations: entity, attributes, and relationships. So what's an entity? And this is now a kind of a pre-discussion about object orientation and full discussion on entity relationship diagramming simultaneously. So make it interesting for you. An entity is an object. So object orientation, believe it or not, is not really that new of a concept. It took the same concept we had before the entities, called it an object, gave it 3 attributes instead of just 1. So in structured analysis and design, entities have an identity, but they don't have states and behaviors. So when we called an entity an object, when we developed object, all of a sudden, lo and behold, fell from the sky, object-oriented design and analysis. Whoa! So the object is the entity, except for now, along with identity, it has states and behaviors. So states and behaviors ended up with the data component and then the processing of the data. So it added processing along with the data to give us, to put it in programming language terms, data members and member functions, or some people call them variables for the data, and functions or methods, messages, methods, or something. It's just generally titled that for the functionality for the processing. So object orientation and the class diagram and the object diagram, believe it or not, are entity relationship diagrams. So you can translate an entity relationship diagram into both. It's a direct translation from entity relationship to class and then also to object. It depends on how much level of detail you're putting on the diagram as to which one you've created. So now you're actually learning UML. So go back to your question, are we going to talk about UML? Yeah. This is actually, believe it or not, entity relationships are, the first two diagrams you would do in object-oriented analysis and design as well. It's the same concept. So for those people who are not familiar with the concept, an entity is an object, essentially. So the same thing, identified by the user's work environment, something that the user wants to track. It resembles a real-world object. So entities, and this is actually the same as if you were drawing an object diagram, show up as a rectangle on the screen. So you see an entity down here, and it looks like a rectangle. It is a rectangle. It could be a square. Sometimes they make them square. Sometimes they make them, long, big old rectangles because then they can put some stuff in there. But it's nothing more than a box with a name on it. And what's the name? It's a thing or an object in the real world within the application context, which is kind of important to think about because everyone goes on. Your first day of object orientation, they think everything's an object. Everything in the real world's an object. The chair, the table, the pen, the mouse, everything's an object. And students kind of get overwhelmed by the concept in some ways. So think about the application context. So if I was building a student registration system, my objects might be students, teachers, classes, maybe also the registration process, maybe, or the transcript, or the, if it's a retail sales application, an invoice, a sales receipt. Well, those are concepts of objects. Those are concepts, they're not physical objects. There is the concept of a registration. Students registering for classes, and you get some sort of paperwork as an output of this process. But the concept is the object, and then the paperwork could also be an object as well. So everything, essentially, from real-world objects to concepts themselves. So it's a set of properties which uniquely identify it as well. Those turn into your data members. And an entity is represented by a rectangle. And the entity relationship diagram, which is what this project box is doing on the bottom. So what's an attribute? These are the data members in a class that describe the object, essentially. An attribute describes the characteristics of the entity. An example, an employee has an employee name, extension, phone extension, whatever, data hire, something like that, maybe date of birth or something. Things that describe. And so then we can have attributes. This is the old-fashioned way of doing it. This is what an entity relationship diagram would look like. In an object diagram, or actually we'd just leave it empty, in a class diagram, you'd put these items inside of the box. And there's 3 sections on the box. So you have the top section, which is its identity. The next section underneath it, if you imagine just a rectangle box, cut and you draw 2 lines across it. The middle section is all these attributes. And then the lower section, sometimes it's left blank, but those would be the methods or the messages that would be passed back and forth between the objects to allow them to communicate. I'm assuming some of you guys have object-oriented experience, hopefully. If not, then this is brand new. In here, though, as an example, using an entity relationship diagramming method, we've taken the attributes and we've attached them to the object or the entity with lines and bubbles. This is like the first way they started doing it. It kind of looks a little, I don't know, kindergartenish looking. I don't know. Looks A little primitive kind of approach, but it's still being used. You still see entity relationship diagrams with bubbles and attributes next to them. It's perfectly acceptable. Or, you can put them inside the box as well. Going back.
The underscore and the budget location, is it
Oh, it's separating words. And you know what? You don't even have to do it that way, but people do this because at least it makes a legal variable name.
Okay.
If you put this underscore in here, it's a start date, so you don't have a space. It's actually transcends from, let's say, a programming style naming convention.
Yes.
Some people actually take out the underscore and capitalize the D.
Okay.
To put two words together. Yeah. It's just a standard.
The location. Oh yeah, because they're 2 words.
Yeah, it represents 2 words. In programming languages, if you wanted to call an attribute start date, you can't put a space in between. You'd get an error. So it's believe it or not, all of this is style, or what do you say? It's you can call a variable anything you want. So it's format, style, best practices in terms of programming. So. Okay, the third component, so we have the entities, the attributes, and then we have the relationships, the third component that we're showing. The relationships are the associations between the entities, and they express some real-world relationship of some sort. So project employs employees, and this is our complicated diamond symbol. You don't actually have to use the diamond symbol, but it is very common to see it being used. So if we read this diagram, we'd see that project and employees are participating. So they participate in the employees' relationship. So this is actually referred to as a binary participation, because we have 2 entities or objects that are participating in the same relationship. So we have a project. And then what we put in here, employees, going back to the name, it doesn't really matter. It says hires, employees, some word to describe the relationship. Oftentimes when you see this binary approach, you don't see this diamond symbol, you just see a line. And they put works for, employees, hires, or something right there on the line. So you can kind of imagine how that might be put together. And so the function the entity plays in the relationship is called its role. And this is the common and the current object-oriented vocabulary as well. So I'm teaching you how to create an object diagram at the same time. It's the same concept, essentially. You just have, the symbol sets are a little different. Slightly different. But. We can have many different roles in the relationship, and each role is depicted by a new line. So if it said project hires employees, we could say project fires employees. Project contracts buildings. Different relationship, actually. Now we have contracts. A building with a project instead of an employee. So. And we basically map out the different relationships. So here's some relationship sets to look at. In fact, here's our multiple roles. So there can be more than one relationship between the entities. So the road and the town. Think of a road and a town. Well, it starts at or it might end. Might be the starting point, might be the ending point. So we have 2 separate, but they're the same relationship between the 2 same entities. Here we have a relationship with itself. It's a recursive relationship that can indicate a role for clarity. Here's an example. We have an employee that works for, or is a worker of an employee. Let's talk about a manager, for example. All of the employees are all employees. Some of them are managers and they manage other employees. So we have a manager who's an employee managing another employee who's an employee. They're all the same. So apparently, I guess the manager is managing himself as well as an employee. So it's a recursive. If you're not familiar with the recursive vocabulary, it's a programming term. Normally in a C or C++ language it would be like a function calling itself recursively. It's a form of iteration. If you're not familiar with iteration, go back another level, call it a loop. Or a circle. So you're going over and over again. So you're looping. And here's a relationship that has an attribute. So we have a client who orders a book, and the order has a date. Not bad. So we have a date that's associated with the orders. This would be like a a person who buys something at the store and has a sales receipt, and the sales receipt has a date and has a number of items ordered and has all the information that's associated with it that belongs to the relationship actually. Yeah.
The old shape has actually a meaning like.
Yeah, this is what's called an attribute. This is the relationship. So the old is the attribute, the relationship, and then the entities.
Okay.
They call it an entity relationship diagram because we have entities and we have the relationships. Yeah, attributes. Yeah. It's the easiest way to remember the diagram is by what's in it. There's only 3 things on it.
Does it have to be directional or no directional?
Excellent question. You're supposed to be able to read the diagram left to right, right to left, top to down, bottom up. Any direction you want, it should have the same meaning. If it has a different meaning, the diagram's wrong.
Already.
Yeah, if you read it this way and said, books aren't ordered by clients, there's a problem. But if the clients are ordering books, that works, but the other way doesn't work. This happens to be correct. But if it doesn't work, then the diagram is wrong. Because you're supposed to be able to read it, and it's supposed to have valid meaning in all directions.
Okay, but can you make it just one direction? Like if you intentionally, if there is no meaning?
You can do that. Yeah. What you don't want to do, though, is provide descriptions underneath the diagram.
Yeah.
And the diagram is supposed to be giving you the meaning of all those descriptions. Yeah. Here's some different degrees of relationship. So we've been looking at binaries. Now we can have more than one. And now we have 3 in this particular case, or a 3rd degree. So we have project that hires contractors that we've seen. And these are all the attributes that are associated with contractor. Contractor has a name and address. And the project has a project name, a location, a budget, start date, end date. And then the contract has a number, value, end date, start date. But we have, the reason why we're using this diamond symbol is now we can connect all of the different attributes and they all get a different spoke. And the reason why the diamond symbol is actually used is because we don't normally go more than 4. This is a 3 degree. If you put another attribute out here, if you put another entity out here and connect it, then you're probably at the highest level you want to be at for readability. Otherwise, this could actually get kind of complicated. A project hires a contractor and there's a contract associated with it. So you could say a project hires, projects hire with an agent a contractor if you wanted to, and there's a contract associated with it. But then that's pretty complicated at that point in terms of the thought you're trying to represent in the diagram. But this one, it's not too bad. It's actually good readability. So. But that is basically an example of the different degrees, 2nd degree and 3rd degree. And we also map the cardinalities in the entity relationship diagram so we know how many participating entities there are. Remember I talked about participation a few minutes ago. In terms of the project and employee, they participate when they employ in a relationship. And it's representing in the diagram their particular role. And we're putting a label on the role. So this would be employees, would be the role or the particular action that's being performed. So if we had, let's say, a bus, and the bus has a number of seats or capacity, or a room that has a number of seats, anything in which we can, or an airplane, a number of seats, anything in which that has a number, that's the cardinality. It's the number of items that are participating in the relationship. So one bus has 32 seats or something. I don't know how many seats are in a bus, but 32 sounds like a good number. So in the diagram we could express 1 to many, or we can express 1 to 32 if there are actually 32. If we have an unlimited number of seats on that bus, we could just put an asterisk, or we could just say many, or any number, or n for any number. So here we have an example of, let's say, 1 to 1. Usually one student might be enrolled in 1 degree program, so that would be a 1 to 1. And we have the arrows indicating, the arrowheads on the symbols indicating that there's only 1. And or 1 to many, so we have 1 over here. One student might be taking many classes. We don't know exactly how many classes. If we did, we could put the number on the line, or we could put it next to it, but we don't have to. We just know there's more than 1. And here we have many to 1, so we have the exact opposite. So we have many teachers, many Many to one. Many students get on the same bus. And they're all getting on one bus, let's say, for example. And then many to many, many students take many different buses throughout the day. They don't all get here at the same time. They don't all leave at the same time. So the many to many going on. Yeah. And that's what's referred to as cardinality in terms of the concept. Cardinality just means the number of, or the degrees of relationships associated in this particular context. So here are some cardinality examples so you can kind of get a feel for a little bit more than what I just gave you. So a person has only one ID book, and an ID book belongs to only one person. So if they only had one ID book, obviously you could change this diagram and give them multiple ID books if you wanted to, or may give them multiple people with multiple ID books. And a person can own many cars. That's true. Some people in the U.S. have tons of cars. Some people have none. But a car only has one owner. Yeah, we have some situations where it's so-and-so and so-and-so who owns a car. But this particular diagram is limiting us. It's making it so only one owner belongs to one car. But as we've seen, houses have many owners. Cars have many owners. So a person can own many houses, and houses can have multiple owners here. So we have a house. Person owns a house. We have multiple owners, multiple houses that they might be owning. And what I'm trying to expose to you here is the concept of whatever you put in the diagram, if you're indicating the cardinality, you could be specifying the rules. So in this particular case, cars can only have one owner. And this is the context of the program or the system that you're designing. And but the house can have many owners. So those are the rules, the business rules that you're employing. Okay, so it sounds like a pretty easy design. We do have some design issues to kind of consider in terms of putting all these pieces together. And it's not really issues, it's more along the lines of confusion or decisions that would need to be made in terms of an entity or an attribute. There is sometimes a decision in that, kind of like, whether something is a functional or a non-functional requirement. When you get down to the analysis, you have to think, well, is it an attribute or is it an entity? How do we want to represent it in the diagram? Which could affect the overall system design, if you think about it. So as an example, should location be an entity or an attribute? You have a project. Project might be at a location. So you could probably use the location as a description or an attribute that's associated with the project, perhaps. Or maybe the locations should be an entity. In terms of, if you want to keep some information about the entity of the location, like location might have, what about space availability, accommodations, physical address, stuff that's, might be properties associated with the location. So,
and can location have multiple projects?
Yeah, and can one project be at more than one location? Which is another question you have to sort of think about if you're building an application that's putting projects at locations, or in terms of the theme that we've been looking at. And the other kind of question that comes up is it an entity or is it an actual relationship? So trying to figure out what's an entity, what's an attribute, what's a relationship, not always clear cut. In terms of the relationship, generally relationships for actions between, they are actual actions that occur between entities. So works for, an employee works for a company, the works for would be the relationship. But what if the employee works for many different companies? With that contract or that agreement or consultancy, would that actually turn into an entity or would that be a relationship? In terms of your diagram, that's another decision. So whatever makes sense in the application context is what you need to do, essentially. Instead of sitting there trying to figure out, is it an attribute? Is it a relationship? It doesn't matter, actually. When all is said and done, does it make sense in the context of what it is you're describing, and are you actually learning about the system, and are you presenting an accurate picture of what it is you've understood about the system that you're developing, which is part of analysis, essentially. Okay, so we've seen some pictures of these diagrams already. Yes?
I just wanted to understand that location concept. For example,
Mm-hmm.
You manufacture cars at various locations, right? So in that case, would that be an entity or attribute? It's a little confusing. And
In that case, I would make it an entity, actually, because we had various locations, perhaps, and in the locations we can keep track of all the different addresses, phone numbers, people who work at the locations, and all the other information.
And can an entity exist without any attribute?
Yeah.
It can.
Mm-hmm.
Okay. I just wanted to make this clear.
Normally, it's very uncommon to see an entity exist without any attributes.
Okay.
Because why would you be? Why would you be? It would be meaningless. And if it didn't have any attributes, it might be a candidate for either an attribute or a relationship. So if we just had one address, where do you live? That location for where you live, it would be an attribute. It wouldn't actually be an entity.
I'm sorry, I didn't get that example.
If the location is describing, let's talk about location for example. If it's describing where you live, so you have an application form. It says fill out what's your address. That would be an attribute for you as a person. It wouldn't necessarily be its own relationship. And there's no information about the location outside of the concept of the location, which turns it into an attribute. But let's say you're talking about the same concept of a location and you're relating it to a project, and we have 5 different locations. That might be an entity. Yeah. That's actually a really good example of the confusion of the design issues that come up actually when you start thinking about it. Okay, so here's some symbols. These are the ones we've seen so far. This is all you get, essentially, on an entity relationship diagram. We have the entity concept, which is, as I mentioned before, the object or the class. We have the attribute that is only really seen, the bubbles are only really seen in the entity relationship diagram. Not normally part of a class diagram or an object diagram. And the relationship symbols, again, not always seen in a class or an object. It's an entity relationship symbol. It's definitely part of the entity relationship diagram, not the class or the object related one. And then we have the lines, and it's very common to see the arrows for the one-to-one, the menus with nothing on it. I've also, you can use a 1:1 for a one-in-one, a 1:***, a 1:n, or a 1:m for many or for any number, n for number, or numbers. You can actually put numbers on there too. The way that you create your entity relationship diagrams for your project is essentially going to be specific towards the tool that you're using and the exposure you've had to this. So this could be a very simple example of your entity relationship diagram. You may also create it using a different style, in a different format. There are no rules. So as for those of you who came in late, I went over the analysis document already. And in there, when it specifies, that you need to have an entity relationship diagram, or you need to have a data flow diagram, pick whatever is representing something significant about your system and create one to actually show that particular thing. You can show more than one. You can put in 20 entity relationship diagrams if you want. You don't have to, though. You just have to put one of each in each one of the categories. So that's an example of what a finished one looks like, including some attributes on the relationship here. So project employees, and has a start date and an end date that's associated with the employees relationship. And the project eliminates aliens. It's a Ghostbusters project, for those guys who remember that movie. And here's the alien, and the alien as a species and an area that's associated with them as an attribute. And the project as a location turned out to be an attribute. Project name, budget, start date, end date. And the employee obviously has some information that's associated with the employee. Make sure the attributes mean something to the particular entity. So for example, over here for the project, you may not for the employee, you may not necessarily want to have like a project start date or an end date. So you want to have only attributes that are associated with the entity of the employee, that are associated or connected to the employee.
And there's an underlying species. Does it have any meaning to that?
It does, actually. These are candidates. If you were building a database, these would be candidates for primary keys.
Primary.
Yeah. You don't actually have to do that, and that's the reason why I didn't really point it out, is you don't really need to do that for your projects. If you were doing a database design, and you were looking at, as an example, the employee, the underlined ID would be a candidate to say, hey, in this diagram I'm saying this would be a uniquely identifiable attributes. And it's just one attribute that's going to be unique of all employees. And so you underline it and say, hey, and they call them candidates actually. Because you don't know if it's going to be a primary or a foreign key or secondary. You don't know what it's going to be. But candidate says, well, it's a proposal that we're going to, it's a candidate, it's an available option for us to make it into a key of some sort. So we identify candidate keys, and then when we implement the database, if we're going to do that, then we would make it a primary key, obviously, for the employee table ID would be a primary key. And it may actually be in the employees table, if we made that into a table, which we would actually do, if we were translating this into a database, then we would actually add the ID to the employees table, and that would be a foreign key in the employees table. If you take the database class that I teach here, I go through creating the entity relationship diagram and then translating this. There's a formula, you translate it into a set of tables, and then there's a routine for how you decide which keys belong, which ones are foreign, which ones are primary, and then voila, you got your database scheme from that. So that's what, actually it's not really a side tangent, it's kind of part of the discussion today. It's why the entity relationship diagram is the data. It's the data model. And people think, oh, it's processing. No, it's showing you the data, and it directly translates into the database, essentially. So where to start? You get your requirements document at this point. That's all you've got, hopefully. And hopefully you have a requirements document at this point. You're identifying entity sets. So a lot of people go through and they go, well, what do we got? We got a student registration system. We have students, classes, registration, and you're kind of looking at it, you're identifying the relationship sets, or the identity sets, or the entities, the objects. And then you describe the entity sets with their attributes. Well, students, you want to keep track of their names, their addresses, their student IDs. And then we look at them and we specify the relationships and the cardinality that's associated. So we say, well, students take classes. And one student can take many classes. And we start looking at it and analyzing it, and then we model it. So I'm going to go through a simple example that kind of shows you how to actually go through this process from your requirements. So here's our simple modeling example. Every department within the company is in only one division. And each division has more than one department in it, and there's no upper limit on the number of departments that a division can have. So we have departments, divisions, employees maybe. So we can, number one, define the entities. Division, department, employees. Sound like a good set? Because every department in the company has every division has one department. So we're talking about divisions, we're talking about departments. We're also looking at actually we have employees, and we kind of threw that in there. It wasn't really part of it, it was an assumption. Actually, it wasn't mentioned in the description, but we're going to assume we have employees working in departments that are part of divisions, maybe, or something. So first step, we identify the entities. Next one, we kind of define the relationships. So the division contains departments. What are the departments doing? They're managing employees. So we can look at the relationship. And then you see, because it's a one-to-one, we left out the diamond symbol. We just put a line between them. And then here, instead of showing it, like this way, we could have written it in a vertical line. We could have gone a horizontal line. Instead, we kind of did a diagonal line just to show you, you don't have to follow. You don't have to color between the lines here. You can create your own method of doing this. Some people, would go this way with it, maybe. I don't know. This makes sense for me, actually. Kind of seems like a little hierarchical, so I'll put it on an angle. But there's no right or wrong way of doing that. And then after we have defined the relationships, we look at the cardinality. And then we see that the division might have many, or might have one. In this particular case, there's one department for many divisions. And we have many employees that work with many departments. When we use the crow's feet, we could specify, and this is where the symbol set comes into play. You can specify many, you can specify one. And going back to my definition of cardinality, it's the one-to-one, one-to-many, many-to-many types of relationships that might exist. So let's take a look at the standard notation that I've been talking about. I haven't really shown you what it looks like yet, but here's an example. Sometimes you see 1 to 1, 1:1, as I mentioned before, and you'll see it like right next to the line. In this particular case, it would have made sense to put it like right here. And it usually ends up right next to the entity box where there's available space. Like I would have put like right here, I would have put like 1 to 1 and 1 to 1 up here, maybe, and 1 to 1 up here. Where you put it on the diagram is up to you. We have the plain old rectangle that's used to represent the entity. We've seen that already. And then we have the line that has a label on it that represents the relationship. And then this is optional. You can put a line through it that says there's just one. Or you can use these crow's feet. And you see in the previous example here that I showed you, we have crow's feet here. Could mean many. This is the exact opposite, which is normally what we see versus this. Oops. Hello. Versus this, which is, you know, kind of harder to understand. This is actually a symbol for one instead of many. So it's actually the opposite symbol. So going back to here, this is more standard to see, and it's kind of like this branches out. So it's like, that's why it's many. And the number N for number, it could be an M as in Mary for many, as M as in Mary, and excuse me, M as in many. So, or N, meaning that there's a cap. See, M for many could mean like many students, which means there's no enrollment cap on it. There's no point where the class is gonna get full or something. But there is a point in which the bus is gonna get full, meaning some buses might have 32 seats on them, as I was using as an example earlier, or some might only have 10 seats on them. So if it's a number, then that's N for any number. So that's how the N and the M's are used. And here's the diagram with the standard notation put on it, where we have one division could have many departments. Or we can have, you know, we can put this on here to kind of represent what it is we're trying to explain. So, this is kind of a way of diagramming it out. Here's some other ones. Some notation examples where we have one course has enrolled one or more students. So we have one course, we have a line through it. We don't have to put the line through it, we could leave it empty. And this is the exact opposite of the symbols we were looking at a few minutes ago, where this, if we had a plain line here, it would have been many, actually. But using standard notation, this is more common to see it this way. And they put the line here to say, hey, we're using standard notation. It's one. Sometimes you might see the line with a 0 on it. If you see the 0, it means 0 or 1. Like there may not be any courses. Which maybe there aren't any buses right now. It's lunchtime or something, so there's no buses. Or the course is not being offered this term or something, so we have a 0. And then the crow's feet, this is very common. You'll see this crow's feet over here a lot, actually, for the many side. So one student is enrolled in one course. Maybe we have a one loan that refers to one book, or one loan that refers to one book that is referred to one loan. So we can read it left to right, right to left. How you put the label on here is going to make it readable. So courses has enrolled students. Students has enrolled courses. Most of the people would read this if you're reading English left to right. However, you should be able to read it right to left, as I mentioned earlier, and it should make the same sense. So sometimes you want to put words in here that can be, like enrolls. Maybe I would have changed that and said maybe enrolled instead of has enrolled. Or takes. Takes. Student takes course. Course takes students. Maybe not. So what the words you use in there are kind of your own choice, I should say. Nothing is really going to make perfect sense read in all directions. So the fewer words you put in there, the easier it is to kind of translate it, I think. So here's a many-to-many relationship example. Any one supplier might supply more than one kind of part. Any one kind of part might be bought by any number of different suppliers. So we have supplies, parts and suppliers with many on each side, giving us that relationship. Here's some more examples. A customer is associated with property. One customer might be associated with many different properties. So you're going to buy a house. What if you already own a house? Maybe you're going to buy 2 houses, 3 houses or something. Hopefully you have enough money for it. Or well, let's change it and say maybe you're going to place an order. So one customer can place many different orders. Teachers, one teacher can teach one class. Hopefully a class has more than one student in it, though. So courses, teachers usually teach multiple students normally. Or we have multiple teachers who also teach multiple students as well. Here's a simple hospital system. And what you're doing is you're modeling essentially the abstract concept of the system. So we have a ward. Think of it sort of a department. Nurses. One ward might have many different nurses in it, and it cares for many different nurses might care for many different patients. Patients might suffer from different ailments, so they don't all have just one thing wrong with them sometimes. You could have one thing wrong with you, or you could have many things wrong with you. One patient might be treated by software engineering. Might be treated by software engineering. No, patients are usually treated by doctors, or software engineers, depending upon what the problem is. So, if they have a computer virus, the patient might actually employ a software engineer. Anyway, back to the hospital example. So you can kind of see how the diagrams can come together in a specific kind of way. There's no generic diagram you can create for any system. You pick what you're trying to show and you diagram it to show the particulars in terms of what it is you're trying to represent. Here's a college system where we have a department that has lectures in it. One department, computer science, might have many different teachers in it, and the department itself might offer many different courses. So our CS department or SC department has many different courses, and then students, tons of students can take many different courses. They enroll in courses that are taught by different teachers. This kind of represents most college systems, I would say, in terms of how the layout is presented. And so, let's see. And that was everything you ever wanted to know about entity relationship modeling. I'm going to go through another quick lecture, then we'll have a break. Well, we'll have like a 15 bathroom break / get something, rest break. For those of you who came in late, you can watch the video, see what everything you missed. A bunch of people just walked in. So lecture 6 gets into data flow modeling. You would think that this would be modeling the data, but as we just saw, the entity relationship is modeling the data. Very clearly, actually. And the data flow is modeling the processing, which is why we have process descriptions that come out of data flows. Based on the notation that systems can be modeled as a set of interacting functions. So we're looking at the functionality now, or the processing that's going on. This is a data flow diagram to graphically represent the external entities. We still have entities, the processes, the data flow, and the data stores. So the processing actually creates the data that we're showing in the entity relationship diagram. So graphical system model shows all the main requirements of the system, the inputs, the processing, the outputs, the data storage. So let's take a look. The data flow diagrams are composed of 4 different components. Just like the entity relationship was composed of 3 entities, attributes, and relationships. Data flows now have data flows, processes, data stores, and terminators. That terminator on the bottom, let's start at the bottom and work our way up. The bottom terminator kind of looks like an entity. It is an entity. It's called a terminator in a data flow context, I should say, because it's the starting or the ending point. Usually it's the ending point. Something turns into the sales receipt. Something turns into the employee. What's an employee? An employee is a person who works for a department at a company or something. Well, it's a terminating endpoint of the diagram, which is how it becomes the terminator, not like the governator or the Terminator, the movie The Terminator. Although termination means end, usually, in English definition, or stopping point, and so which is essentially the same thing in a data flow diagram, so it is a true definition of it. The data store here, sometimes we see it working our way up. We see it as this rectangle, but this is often confused. So sometimes they leave this side, most of the time you'll see this side open too. You'll just see two lines with the name of the store in between. And a data store is a piece of information. It's a piece of data. It's not like a store, like a drugstore, like a physical location or something. Instead, it's just like, we're going to save this for later. Think of store like a temporary memory, or like a log file, or like data stores could be text files, they could be database entries, they could be any piece of data, a variable, anything that would represent the storing of a piece of information, like a name as an example, a telephone number. The word name is the name of the data store, the name of the terminator, the name of the process, the name of the flow. And I'll get an example in a few minutes and we'll put the pieces together. Process bubbles are functions, which is what we're modeling. The data flow diagram is all about the processing. Sometimes we put a number on the process bubbles, helps us easily identify them. And then we have the data flow, which is the line. And the data flow has basically a name usually associated with it as well. Hello. Oh, there we go. So here's our example diagram with our key over here. And the key is showing us the processes, which are the bubbles, the data flows, which are the arrows, and then the data store. And this is what I was mentioning before. Both ends are open. We open both ends because it's really easy to kind of write it too small, accidentally fill in both sides. This is not quite as clear when we open up just one end than when we open up both ends. So this is what the standard kind of notation sort of looks like. But you will often see it with one end closed because they'll put a number out here and they'll put a box with a number in it, and the box will be like number 1, number 2, number 3, because you can keep track of your data stores as well as your processes. So we have these customer request comes into a processing bubble, and then the request goes to another processing bubble, and that request goes to another processing bubble, and then it comes out. So usually in a data flow diagram, we're going back to processing to processing to processing. We're not showing relationships, we're not showing entities, we're not showing attributes, we're just showing the processing. So it's the flow of how the information or the functionality of the system is actually working. Which is interesting because most people go, data flow, it's showing the data of the system. Nope. And that's what the entity relationship diagram is doing. Here's a good example. This is your typical information system. Models almost every system out there in terms of generic functionality. What are we really doing in an information system? We're taking input, we're processing it, we're creating output. And what is the output? It terminates into something. Let's talk about a retail store, because most people are familiar with buying something at a store, so you walk into the store, you put some stuff in a shopping cart, you check out. So let's talk about the checkout system. Here it is right here. We take all the input. What's the input? The items in your basket. The person scans them over, a reader, and all this stuff, all the information from all of these items that you've purchased come into this transformation, like this bubble here, this processing. What does the processing do? It says you have 5 bananas, they're $1 each. You have 2 apples, they're 50 cents each. You have whatever you're buying in your shopping cart. Quantity is put in there, the item, the price of the item is put in there, and let's say sales tax and some other stuff is added in there, all that good stuff. And this is our transformation, that we get this output that comes out of this process, and it's our sales receipt. This termination here, this terminator is our, here's your receipt. Would you like it in the bag, or do you want to take it with you? It's your receipt. And in the meantime, we have this thing called a data dictionary that helps us out. Where do we think we're getting our sales rate from? What about our current price list? Or what about, you get a 10% discount, it's on sale today. Okay. So the data dictionary is a data store that's coming in. And the data store we can tell because it's open on both ends here. It's not a terminator, it's a data store. And we have usually what's referred to as data stores and data dictionaries. The dictionary is stuff we already have. And the directional arrow is going into the transformation button, which means for the local county and the state that we're in, we have a sales tax rate, and we're providing it from this already information that we use for every single transaction or something. We have this information stored. It's coming in from the dictionary, which is essentially the terminology for that. We could have something going out into the dictionary or them getting out to into the store, and that's what our next example. Actually, we have some more examples showing, well, it's coming up soon, showing how the data can go in and out. So the terminator symbol is the external entity with which the system communicates. The directional arrow says it's producing it. In our particular case, this was our sales receipt. You know, the receipt everybody throws away, or they look at it and they go, hey, I only bought 2 of these. It says I got 3 of them on here. You know, or something. Oh, she didn't charge me for the bananas. Oh, cool. You know, and you feel like you got something for free. And we did. So typically the terminator is a person or a group of people or an outside organization or a agency, government agency of some sort. In my particular case, I related it to a retail sales environment. Let's say it was something else. It might turn into an employee. An example. You send your resume in. The resume gets, you know, picked, selected, you know, and somebody else comes in and says, hey, we're looking for someone with programming experience, or we're looking for someone with this type of experience. Output, we got an employee. All of a sudden we hired some guy, he turned into an employee. We could do the same thing, and we can get, you know, citizens go to the DMV, and they take a test, and they, I don't know what you have to do these days, a written test, an oral test. No, you have to do a driving test. And you get a driver's license, and then you get a licensed driver. So we have entities like licensed drivers, taxpayers, students, teachers, employees. They get created as terminators as well. And then they might show up on an entity relationship diagram showing how they work with the system as well in terms of how they're producing the data that's coming in. So here's an example of some terminators with a process bubble. And now we have a Ministry of Education parents on one side, University Information System in the middle that's providing the information. What are they doing? They're making available study records to parents, let's say. And then the parents are requesting. So we have the directional lines of the parent requesting, how's my child doing? And the university system spits it out. Wrong direction. Or over here, you know, Ministry of Education or anything else, you know, some other institution or some other government agency, perhaps, as an example. Enrollment data. How many people in the United States are going to school? You know, the government would come back and say, well, student enrollment data, here we go. Throughout the entire United States, we have so many colleges and so much information and blah, blah, blah. How many foreign students do we have? I don't think they really even know, actually. I'm sure they don't even track this information in the United States. They do?
There's an organization called
The Department of Homeland Security?
No.
Oh, there is an official department in the United States that tracks education?
Yeah. It's not official. It's an NGO.
Do you work for that department or something? No.
I did some research with them. So that's how I know it. They have accurately from which country and how many students.
Oh, really?
Percentage growth year by year.
Oh, cool. I've learned something new today. We do have a department. That's good. Oh, we'll stop saying we don't. Here's a library system. And this is a good example because it's showing you a simple, and we're going to build on this. So far, we've just seen one processing going on. Not so big. What we want to do is actually show the processing, which is the focus of the data flow diagram. So we have a library user, an entity. Okay, it's written this way. It's written this way so we can connect all these lines to it. If we wrote it this way, you know, we'd add smaller space to put the lines in. So it's a rectangle. Whichever direction you put the rectangle in, it doesn't matter. They might have a library card. The library card information is going into this bubble that says issue library item. They might have a requested item. I'd like to rent or do a loan. I'd like to borrow this book. And here's my library card. And then the librarian is going to issue the item. Okay, here you go. What do they do? Stamp the book and they say, here's due back in 2 weeks. Okay, here's the item issued, goes back. And the library person who's doing this, who's issuing the library items, might be working with a library assistant who might be coming back and say, hey, what's 2 weeks from now? It's I don't know, what is 2 weeks from now? It's almost 1st of July, I think, at this point. So, so the return date comes back in. So it's not really coming from a data store in this particular example. It's coming from an entity that's out here, and this is the entity or the terminator. So entities and terminators are the same thing, and you just get that concept down.
Can it be a system?
It could be a system. And going back to when I said entity-based system diagrams, entities are person, places, or things or objects in the real world. So anything that's an object is an entity. It's also a terminator.
Yeah, when you said the Ministry of Education.
As a concept, it's a government agency.
Yeah, but you actually talking to that database or that system, storing back information.
Actually, that's an organization. It's not what they call it in the States, but it's a government facility. It's a group. It's a group of people, ministry that regulates. Yes.
In our previous example of shopping cart, right? We
Uh-huh.
had input and output.
Yeah.
So input was the items that you want to purchase,
Uh-huh.
right? And output would be sales receipt.
Yeah.
And then the terminator is also sales receipt. What's the
Yeah.
difference between output and terminator?
The output would be the information that's going on the sales receipt.
Okay.
We have the cost, the tax, the total, and maybe the return policy is on that sales receipt, usually on the back or something or the bottom. The date, the time, excellent. All that information is the output that's coming from this particular process that's terminating. It stops at this entity, and this entity is going to be called the sales receipt, or the invoice, or if it's a shopping cart, it could be a confirmation email or something that comes to you and says, "Hey, this is all the stuff you ordered. Is this you?" No, or maybe it's PayPal or something in a modern day world. So this, and what we've seen so far, has been showing a simplified version of the data flow diagram. This is more realistic. Because here we have issue library item. Kind of generic. This would be a very high level overview of the system, which is why it's called library system up here. Example of the library system. Here's another example of the library system. Looks a little different. It's actually the same thing. It's from a different contextual level. This is higher up. This is showing you one big process called the issue library item. So let's take that and divide it out into sub-processes. Now we have check user. We have check the item, update the user details, and then issue the item. So here's our original issue item, but we have all these other processes we added to it. In this particular example, what happens when the library card gets put in? In here, it's very abstract, and that level of detail is very high because we don't know. Is there a check library? What if the book doesn't exist? What if this is a wrong book? What if this book is not allowed out of the library? We have none of these processes represented. So here we put the processes in. So we still have the library user, we still have the library assistant in here, and library assistant is still just doing her return date. But over here we have the library user, we have the library card that's coming into a check user. And then from the database, this is the data store, it's open on both sides. We have a process that comes in and says user details. Give me the user details. So it says, hey, here's a B hacker. Oh, okay. Know what? The user information that came from the database says you got 5 books out. We're not going to let you borrow any more books till you return those items that you still have out. And that's usually what ends up happening to me when I go to the library. I borrowed those items. Oh man, I don't know where they are. Okay, so I'll go get them and return them to you. And then the process stopped. But let's say the process was good. Let's say I didn't have any items. I went home, got all the items, brought them back. Now it's gonna, well, let's see. Let's check the status. The user status goes into, okay, we're good now. Request an item. This is the item I want. And maybe from the item database, the item details come up and says, hey, yes, we do have this book in stock. It is right here. We have one. It's okay to, it's okay to check out. If it's okay to check out, then I'm going this way, or I'm going this way, or I'm going maybe one first, maybe the second. We have no indication of the exact order that this is actually being performed in. We just know that this process here, this check item, is going to work with this user update. because we're going to update eventually. We're going to send information, update the details to the database, and then the database user details is going to come out of it. Say, yes, okay, so B-Hacker wants to borrow this book. The book is in stock. The B-Hacker's got a good account. So loan her the book. So update the user details and say, hey, you're going to update and you're going to borrow this book. Okay. And then down here we're going to say, we're going to issue the item. We issue the item and the item ID comes back up. So it can also be updated in the B-Hacker account to say that, yes, she borrowed this book and it's due back on this particular date. Over here that came in from the library. And then we have the item database that can be updated to say, hey, you know what, take it out of inventory. It's already been borrowed. B-Hacker's got it right now until she returns it 2 months down the road or something, way after the due date. So this is essentially what you're doing when you're creating a data flow diagram. This is the level of detail that you're doing for your project. This is what your project data flow diagram is going to look like. Something very similar to this in terms of the level of detail. Yes?
So what is the terminator in this diagram?
We have two terminators in this diagram. The same terminators we actually have in this diagram. We have the library user and the library assistant. It's just the two people that are working with the system. So you might think of it in terms of entities as in terms of people. And they could be objects, people. And then we have two data stores. We have a user database up here. And we have an item database, two different databases. You could have called them tables, or you could have called them stores. It's common to see them called user store, item store, because the symbol's a store. It's a data store, but maybe we don't know if there's a database yet. Or maybe there is a database, then we can actually call it a database. If we're technically using a database, then it's probably better to call it a database, I would think. Yeah, so. These are very good questions, by the way. Keep them coming. Because it tells me what I've forgotten to say or what may not be clear. So I love the questions. Okay, so here's a simple math problem to kind of show you how the processing works and how the flow should work. Problem with this slide is I probably should edit it. These boxes, I don't know if you can see. Yeah, I can kind of see it. It's kind of a fade. I shouldn't call them boxes or circles. These are the process bubbles. They're kind of very lightly putting my mouse over them. There's 1, 2, 3, 4 process bubbles. And they have, the labels are coming out, but the lines are kind of faint, depending upon how you're looking at it. So what do we have? Let's go back to algebra. A plus B times C plus D plus F. So if we take this order of precedence going on, we have A and B coming into a calculation, and we have C and D coming into a calculation, and we have the two of them being multiplied together, and then we have an F being added to it. So here's our A, B, and here's our C and D down here. We have add 1 and add 2. There's two separate functions that are going on in terms of the processing of this particular equation. And add 1 is taking and adding these two together, and add 2 is taking and adding those two together. And then we combining them with this multiplication. So we have the sum 1, sum 2 coming out into this multiply button. Some people are math people, so this is why it kind of shows you how to process a math equation. Apply it to the system. It's the same concept, is what I'm saying. So we have the product P that comes out of the multiplication of the sum 1 and the sum 2 that comes together. Here's our product symbol here. And then we have F. Where did F come from? I don't know. It just showed up out of nowhere. So the product is coming in to add 3 because we have an add symbol coming on here. And F is just coming in, so there's nothing. F's not coming from anywhere. If you notice, A and B aren't coming from anywhere either. So here we had it coming from somewhere. We may not necessarily know where it's coming from. And if we don't know where it's coming from, then we get something sort of like this, where we have arrows that don't come from anywhere. Or we might be able to put a label on it that says customer request. What customer? I don't know. You don't have to put the terminators out here. You don't have to say where it came from. Where it's going to, we don't know where it's going to either. It's going somewhere. Just because what we're showing is just the processing of what we're concerned about showing. Problem is people get overwhelmed. One of the biggest problems in terms of creating these diagrams, all of the diagrams, is knowing when to stop, what to show. You're showing something significant, hopefully. Otherwise, you're not going to bother creating the diagram. And what you're showing is going to be very particular in terms of the processing or in terms of the data, in terms of some component. And you're going to leave out unnecessary details. And we don't care where A and B came from. We don't care where C and D or where F came from. Or we don't know where the result's going to either. So we just have this add 3 with the result coming out this way. And then we leave it at that.
Yeah, I think that also depends on the level of the diagram. The more conceptual, you want to show something.
Yeah, like here, we have issue the library item. Issue library item, well, that's actually 1, 2, 3, 4 items. 4 degrees of processing, not 1. Well, we took all this, we put it into 1. Now we spread it out into 4. That's kind of okay, but you're not showing anything about the issue library item processing. It's 1, 2, 3 going into it. That's more desirable because now you have it clear in terms of how you're representing it. And the concept of diagramming, going back to what I originally said before most of you showed up, is we're performing analysis. And our analysis task is to learn about the system. And then to learn about the system, we can learn a little bit there. We can learn a lot more like that. So the deeper you dig into it, the better you understand the system. However, that's easy to understand. Not quite, but it's still manageable. If you go further down, you can make it so that the diagrams aren't understandable either. You could take it to an extreme and defeat the purpose of the diagramming, actually, and complicate the system even worse. So there's a fine line between how much level do you put in the diagram, what are you showing, and is it comprehensible, or is it way too much? Is it overload? Which are some of the things you kind of have to think about. And so there should be a purpose, hopefully, to each one of the diagrams that you're creating, outside of getting a grade for the course. In terms of the project, there should be a purpose, and it should relate to requirements. And if it's not in the requirements, it's not in the diagram. It's part of the process of the system that you're supposed to be representing. I have had situations where I have seen diagrams that contain components that weren't in the requirement specification. You're like, oh, where did this feature come from? Not in the requirements, which is interesting. In fact, in the real world, you see diagrams with features in it that aren't in the requirements. Oh yeah, we haven't talked about the database yet. Oh, well, is this system going to have a database? And sometime before the implementation starts, we probably should decide on that, right? What's in the system? Hopefully you have it in the requirements. Otherwise, you're not getting paid for any of the efforts. And it's not really part of what it is you're building. It's just an afterthought. And no afterthoughts are allowed, essentially. All right, so the data flows. We've looked at the terminators. Let's take another closer look at the data flows. And these are the data flows, these lines here that are connecting all the numbers are creating the processing for us. So they're usually used together with processes. So we usually see one process going to another process, going to another process. So they're used to connect the processes, indicating that the data items are moving from one process to another. And so in our example here we have study records. You applied to a university for enrollment. When you want to go to ITU, all right, send us all your transcripts of everywhere else you've been. Okay. And we divide the records out and we say, okay, we have some qualified records, and then we have some failed student records. Let's say some of them are qualified for admissions and some of them aren't. So let's take the qualified ones, for example. We sort the records out and we send them out and we say, okay, now you're in the MBA program, you're in the CS program, you're in the SE program. And the sorting process finishes the application, let's say, and it creates a student record of a good sorted record, and we have goes out to sorted records, and maybe out here we have another process that maybe sends a congratulations, you're now accepted at the university, blah 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 kind of thing, right? Or down here we have the give recommendations, maybe, and this comes back and says recommend records with recommendations that come back because these are failed recommendations. And this processing of the flow comes out, and maybe a letter gets sent out that says, hey, you know what, go back and take and get a bachelor's degree first. You can't get a master's without a bachelor's or something like that. So recommendations that occur. Yes?
Why did you use like the decision box or the triangle where you can ask qualified people?
Actually, it's a good question. It's a very good question. You know why you don't use that? Because we're creating a data flow diagram and not an entity relationship diagram. The reason why I say this is a very good question is because the common error is to lose focus on what it is you're actually diagramming. And you missed the beginning part when I said structures, analysis, and design separates out processing from data. And the diagramming techniques are separated into these two components. One's the entity relationship and one is the data flow diagram. And people, they see the word data inside this data flow diagram description. And they think it's talking about the data when it's really talking about the processing. And the entity relationship diagram is all about the data, and that's actually used to create the database. So you show the data and how it's being created and organized in terms of the overall database scheme that's going to be presented on one side of the fence. On the other side over here, you focus on the data flows. And you're not showing any relationships. You're not showing any entities. You're not showing any attributes associated with the data. All you're looking at is the processing, the flow of how a piece of data goes from point A to point B and how it's created. So it's kind of like if you stay focused on the purpose of the diagram, there should be no relationship. There should be no decision making.
Is this something of a sequence diagram?
Processing is sequence if you think of it that way, and it does not translate into a UML sequence diagram. The entity relationship diagram translates into two UMLs. And this is a repeat for most of you who were here earlier. It translates into the object diagram and the class diagram. Because entity relationships focus on entities. Entities, the newer term for that is the object. So that translates quite well. Data flow doesn't translate at all. It loosely can be interpreted, and you could create a sequence diagram, a UML sequence diagram from this, but you have to start fresh. You have to actually you can use the same logic. It's showing you a similar logic. It's just showing you it in a different fashion, obviously. Because this isn't going to show you the sequence of the events that occurred. It's only showing you how one process leads to another process. How do we know that this happened before this? That's not the focus of the diagram. We can't put the sequence in this diagram. If we did, we're changing the nature of the diagram. We're changing what it is we're composing here. It's like if someone says solve this problem to this level, and you take it to a different level, you haven't solved the problem correctly. Or if you haven't taken it to the right level. If I said create a data flow diagram showing how the processing of this particular library system functions, this is the process. If I said create a sequence diagram that shows the sequence, I'm going to create a totally different diagram that's not showing any processing, it's showing sequences. Which is kind of the art and science of software engineering. We show the data, we show the processing, we show the sequences, we show the contextual, how the object sits in a contextual environment. We show the logical structures, the physical structures, the networking structures. And there's not one diagram that's going to show everything. And so we pick and choose depending upon what we're building, the types of diagrams that we're going to use to represent the system. We're doing this because we're trying to analyze the system, learn about the system. All this work goes into the design. So we're doing our analysis to lead into a design document. The de facto standard for systems analysis and design is to create an entity relationship, to create a data flow diagram, and then build UML from that. Even if you're taking an object-oriented approach, you normally start at the lower level, and then you can build. From here, you can't translate that into any UML. But you can see you're going to have a check user process, and you're going to have a check item process, and you're going to have a user detail, and you're going to have all these processes, and what ends up happening is you write process descriptions for them. So each one of these bubbles turns into a process description, as we looked at in that template I showed you before I started. That kind of went through each one of the areas of the analysis document. The next section underneath this one underneath the design is to give me process descriptions. You create the process descriptions. Then you could do a sequence. You can do a UML sequence diagram.
Do an activity.
Yep, an activity diagram, and you put all those processes in the activity diagram. So you're not reinventing the wheel. You're creating a repository of your processes and your data. You're collecting all of the information that you need, and you're reusing the information. So let's say this was process number 1, this was process number 2, process number 3, which is why they're sometimes, most of the time, labeled. Then you can say process 1 leads to process 2, leads to process 3. And so now we know that the check user, in terms of the activity, if you're doing an activity diagram, or if you're doing a sequence, you could say, before, who's to say the rules of the system shouldn't work backwards? Who's to say we shouldn't check the item before we check the user? Personally, I would save a lot of time. In fact, I hate it when shopping cart applications, they always check the user first. Why do I need to log in to your system when I don't even know if the item that I want to buy is in stock? Why do I want to go? That's because they want to capture your information. They want to know who you are. They're trying to data mine you. But that's a different story. They should just check to say, hey, some actually don't. Some shopping carts allow you to add items to the shopping cart, get it all ready to go. And then when you want to check out, then they'll go, let's check you as a user. Have you bought anything from us before? If not, okay, here you go. You got to sign up here. Just quick and easy. I'm just going to ask you for everything you never wanted to give us before, but now you have to give it to us. Fill out all this form, and collect all your data so we can mail you junk mail and stuff. But who's to say that the rules of the system work in a particular sequence, or that the activities go? The data flow diagram is not going to tell you that, which is why we have to create a sequence diagram now. We have to create an activity diagram. So remain focused on what the diagram is supposed to be showing, and then you've got it down properly. And that was a long answer to your question, but it was all the stuff I had to say anyway. So killed a couple birds with one stone. So I used that expression, and some students didn't understand what that meant. Kill a couple birds with one stone. See, you kill more than one bird with a stone. You guys get that reference?
Yeah.
Okay, good. Okay, good. It was a different group. I don't know. It was actually American students who couldn't understand that. They're like, what do you mean? You're going to throw stones at birds and kill them? It's like, I don't know. I like to use expressions, and sometimes I look and go, it's like, okay, so you guys heard of a Rolodex? Yeah, Rolodex? Well, because you're graduate students, maybe you're older. Young students today, they have never heard of a Rolodex. They know address book. They know to look things up in an address book because they have it on their mobile devices and all of their PDAs and stuff. But the concept of the old-fashioned Rolodex, the wheel that had the cards in it, they've never heard of it. Yeah, I don't know. It was just the other day. I was in an information systems class, and I said, like the Rolodex. And then I see them Googling Rolodex. Like Rolodex. I'm sure there's at least one person in here who's never heard of a Rolodex, probably. I don't know. For that particular case, it might be just vocabulary or something, but anyway, let's talk about, and then we'll break in a few minutes here after this lecture. Important points about data flow diagrams to keep in mind. I gave you the most important one already. Keep focused on what it is you're actually showing. Next one is the data flow should carry one type of information. So you got to break out the types of information in the flow per type. Which is why this diagram here is not as good as this diagram here. However, they're both showing the data flows themselves. They're always showing one type of information. This is the problem when the processing is very abstract. So we're still showing the same type of, we still have these three lines here. We still have those two items going in, two items going in. We still have that one data flow going out. It's the same diagram. Here's that one data flow going out. Here's the two items coming in. And each one of these. What students have a tendency to do is they put, this is actually kind of vague. Update details. How many times is that update happening? We don't know. That's why I say it's vague. What details are we updating? We don't know. I don't know. Is that the name, the address? What if the customer changed their address, the library user, and we're We don't have anything in here to show anything about the address update, or telephone number update or anything like that. So do not name the data flow as student and professor and administrator. That's very odd. I mean, if you were writing a university system and you said student records, but you said student instead, student information. Well, it's better to say student records or something. So the data flows can carry a composite data item. For example, university member, which may consist of 3 components, a student, a teacher, and an administrator. And this composite item, in fact, this is not incorrect to say update details. This is a composite item of all of the details that we're updating. It's just not showing every detail individually. Yeah?
For some reason I thought they were updating the user ID.
Well, they might be.
The item ID for each one.
It might be. But this diagram's not going to tell us that. It's not even going to tell us what we're updating.
Yeah, it's not clear,
But it is kind of clear that we're going to update some details, isn't it? Yeah. Which means that process is going to lead to some communication with that database. And then we got to go back and figure out what kind of communication is all about. That's another diagram.
When the user ID goes in,
Yeah.
they take the user details with the user ID from the database.
And the data flows, they show directions. We got arrows. Every one of these diagrams has got arrows on it. These are the arrowheads. Most people know arrows. Bow and arrow. They may have never heard of a bow and arrow. In fact, there are some U.S. students never heard of a bow and arrow. You guys know what bow and arrows are? Archery? Yeah. They don't have those in video games. It's only guns. You ask a 7 or 8-year-old about a bow and arrow, they have to think. They've never heard the word archery before, and they don't know. But if you say rifle, handgun, machine gun, oh yeah, Uzi. Because the video games, they use guns. Everything's a gun. So we have knives, bow and arrow. We have other weapons, but we're waiting for the video game to have bow and arrow. There's Robin Hood, but how many Robin Hood video games are there? Anyway, okay. They have arrows, getting to the point now, you'll never remember. Now you won't forget, everything has an arrow. I do see, oftentimes, students turn in data flow diagrams, there's no arrowheads. There's just lines. But the arrowhead is actually extremely important because we're showing the direction. Showing the processing that this goes to this, and there's a connection. No arrowheads in a entity relationship diagram as we've seen. We have cardinality. We have no cardinality in here either, so don't try to put cardinality on here. Don't put relationships on here. No relationship symbols. No attributes. No attributes. But the only thing that we can put on here from that would be an entity, and we're not going to call it an entity, we're going to call it a terminator. So we do have the ability to put terminators on here, but we don't have relationships between the terminators. We create a different diagram for that if we have that. So here's our flow examples, and here's some, this is the advanced data flows. And as I mentioned before, we can't know which one happens first, but we do know that student records can go to 3 different locations. And we actually show the flows using this type of symbol. And this is not the crow's feet in an entity relationship. This is student records going to the faculty offices, also going to the university student offices, also going to the professor. We have 1, 2, 3 going. And we connect them here. It doesn't mean that this one is going this way and first, second, or third, we don't know. We can label them if we wanted to, and then we can discuss them in a sequence. Here's the opposite where we have converging data. So we have student records from the student, and I mentioned before in the previous slide, it says don't label your flows student, professor, administrator, so this is not desirable, but it's actually labeling where it's coming from. So we're saying that this is for illustration on the converging data. So we have the student, provide student data from the student, provide student data from the professor, from the administrator. All goes into this classified data. This would be like if you were applying for a scholarship. You have your application records, you have your letters of recommendation, you have your, I don't know, community service records or something, or I don't know what else you might have, and it's all going into this application or something. It's a result, so we have 3 going into 1 instead of 1 going into 3, essentially. And we can see by the arrowhead, we have an arrowhead here, and we have arrowheads 1, 2, 3. We don't put arrowheads on both sides. There's no arrowheads on both sides here either. So only one end of the line has an arrowhead on it. You will be tempted to put arrows on both sides. But it doesn't flow in both directions, does it? Otherwise the system just is like Jello. It just sits there and goes like this all the time or something. I don't know. Here's the data and processing itself. Data flows do not answer many procedural questions. They don't try to answer procedural questions. Because a lot of people will try to do a sequence diagram instead of a data diagram. You're not doing a data flow diagram, doesn't show any sequence. So A and B go into P, the process. And then we have C, D, and E that come out of it. Who knows if A goes to C, A and B go to C, what out of P goes into E? Who knows? We don't know. Can't know. Not for us to know. A little thing about data stores to keep in mind. The data store describes a single or a set of data items. Example might be a file, a database, and anything can be stored as a store. It could be a temporary piece of information that's stored in it's just one word or something. It doesn't necessarily have to be in a complete file of stuff, but what is really a file is just permanent storage of something. So don't assume it's a database. Graphical representation, one of the following representations can be used. Only give the name of the store, while you can give the name and a number, perhaps. And if you give the name and the number, here's the examples here. All of the diagrams I've been showing have been using number A, which is the open, and it's just the name of the store. You could take it a bit further and label the stores themselves. If you label the stores, people do this for databases. And it's generally tables. So they can go table number 5, which is the student records table. Table number 6. And then you can just refer to the numbers instead of the names. And then you can go, well, number 5 is always number 5. What data store is at 5? Oh, okay. And then you can keep track of things a lot easier. Is that table names or table indexes? Or was that first name or last name? Or maybe first name and last name all are in the same table. So you could put number 5 on there, and that would be, the student records table, and now it had the first and the last name associated with it or something, all in the same number. So this is not necessarily an N associated with an item that has to be unique. You can have 5 N's. An N could be 5 on every one of your symbols, let's say. It's all coming out of the same table. So what you do is you provide a legend, and the legend says, N is equal to the table. And all of these data items are coming from the same table or something. It's all part of the registration process or something. And then we have store connections that go in and out, as we've seen so far, just to iterate the point. So stores are connected to the processes of the data. So data flow to a store from a process means that you're writing or updating to the store. So from a process to a data store, you're updating. And the data flow from a store to a process means that you're reading information from it. So you don't actually have to put get student information. Write student information. It's supposed to be self-explanatory, which is why sometimes you see these diagrams and they don't have anything written on them. Because you can tell it's a read, it's a write from the direction of the arrow. But it depends on your comfort level and the level of clarity. A lot of people who don't want to make assumptions, so they'll put it in there. And sometimes they'll put, just the word write or read. Their store, study records, read, go to faculty offices. Professor writes study records. So you can put simple words on there, or you could just leave the words out, and it could be logically assumed, essentially. And then we have the contextual levels. As I mentioned before, that other one I showed you with the, let's go back real quick. That would be a contextual level diagram. That would be a lower level system diagram. By contextual means we're standing up, and I always use the helicopter airplane approach. The higher up you get, the less you can see. The more things look like blobs, whatever. Just pictures, images. Can't tell any details in it. So this is the 100 feet above the ground, or 200 feet or whatever, high level. 25,000 feet from above the earth, we see, well, what do we see? You know, when you're in an airplane, you see a lot of water, that's for sure. Water, and sometimes you see like buildings and stuff. You can see populated areas. Actually, the interesting thing is you can see the land laid out, which is interesting. You cannot see that when you're on the ground. You can't see that at all. So that's why you do context diagrams, because you can't see everything you can see from the airplane on the ground. So that's why we have maps. So we have the source, data flow 1, data flow 2 going into a system, and then we have data flow 6 coming out. And now we have this new word, sync. Sync is nothing more than a terminator that's a data store. So we don't have any more of this open data store box. We've decided to call it a sync. So it's a collection. So imagine a kitchen sink. You put this plug in the bottom of it, or a sink in the bathroom. You put the plug in the bottom of it, and you can fill it up with water. We're filling it up. It's a sink that we're filling up with data. It's going to turn into a data store of some sort, but it's terminating, and we haven't specified it as a data store. It's a sink because it's got multiple pieces that are coming into it. It's being filled up, and it's actually a terminator or an entity, which is why it's actually in a rectangle symbol rather than a data store symbol. Data stores are single pieces of information. Each one of the pieces in here, this sink is full of data stores.
Okay.
The sink is being filled up with data stores. But we're not calling, this might be actually labeled a database in the future.
And that will become a terminator.
It is a terminator, yeah. It's already a terminator. It's an entity, it's being composed into an entity. Think of the sales receipt. The sales receipt terminator is a sink. What do we have in there? We have the date, the time, the items, the sales tax, the person who rang the person up. We have all that pieces of data store information that's in there and throw it into the sink. Put the plug in the bottom, fill it up. And then we use it as a whole. Use it as a sink. Which is why it's called a sink, which is where the word comes from. Here we go. Here's a lower level. And when I mentioned the lower level one in concept, this is what I'm talking about in terms of the numbering. Not a sequence. Look, we have data flow 1. Goes into process 2. We have the data flows that have 1, 2, 3, 4, 5, 6. No particular order. They're just labeled by number so that we can refer to them instead of by their full name. Processes are labeled in their own sequence. Here's our data store down here. We didn't put a label on that. We could have if we wanted to. So that's just another example showing you the lower level of detail. And that's equivalent. These two here, this one and this one, are equivalent to what I've been going back to here. This one and that one.
And this one.
Yeah, that's the higher level. That's the lower level. And so here we don't have the numbering. We could put numbers on them. You start adding more stuff to it, it starts looking harder to read. There's readability to consider. That's why some people don't like to put the numbers on them. In fact, you'll see it very common. You'll see the process bubbles with numbers because those you do have to track. But the data flows, you won't put numbers on them. You don't need the numbers. Some people like to put the numbers on there. Number-oriented. List people like to put the numbers on there. Non-list people don't put the numbers on. You guys know what list people are, right? People that make lists. Sometimes I said list people, and somebody else said, "What? What's a list person?" You know, you're on the list. To-do list. It's like, okay, you guys heard of Type A and Type B personalities? Yeah. Those are Type A's are list people. Yeah. Type B's don't have lists.
But you don't want to.
I don't want to go there. No, Type B's have lists.
No, Type A's may not have this.
Not all Type A's have lists. You're right. I'm a Type A. I don't have a list. I don't have it. I don't have any lists. I'm very organized, though. And what throws me off is when someone messes with my schedule. They say, "Hey, you know what? We're going to fit this." Oh, no, we're not. No, we're not. I'm Type A. There's some type A people that make lists and then they make lists just to cross things off of the list. Yeah. Those are the same type of people that would do this. They would number the order in which the data flows are. And then when I look at this as a type A person who doesn't do lists, I don't like it because how do I know that this is the right order? And I'm looking at order, and this isn't really telling me order, but I think it's telling me order because I see order. I see 1, 2, 3, 4, 5, but it's not an order. There's no order to this. So the common interpretation when people see the numbers is that there's some sort of sequence. No sequence in that data flow diagram. I'm not showing you sequences. Here looks like a sequence, but it's not. It's a process. We have, and this is reiterating the point of a data store turning into a data sink, as I mentioned before. We have the data source. Also looks like a terminator. It's the source of the data. So it's not a data store. We have the processing that occurs, and this is in yellow. I don't know why it's in yellow. It's just showing you yellow. No significance to the yellow or the blue lines. We have the data source going into a process that's creating a data store, and the data store is going into a process that's terminating in a data sink. This is a terminator, this is a terminator, these are processes, that's a data store. And we see the kind of, looks like a sequential flow. It's assumed, and we're looking at this like, but it's really a process. We're assuming because of the arrowhead and the directions that it's flowing in the sequence, but it's not meant to be a sequence diagram. Here's some other data flows in terms of the possibilities. We have a process that is needed to exchange data flow between an external data source and a sink. So here's the external data source, here's the sink, and the processes in between. We can have a process to a process. We could have a process, we could have a source to a sink. Well, normally we would have a process in between. But we don't have to have the same combos. We can have a process that's needed to update a data store. So we have a source, process, data store. We could have a data store that has processes for a sink, and you need to present the data from a data store. Or a process that's needed to move data from one data store to another. We can have a data store going to a process to a data store. Unlike the entity relationship diagram that we saw earlier, we never have two entities together, because entity relationship is only showing three things: entities, their relationships, and the attributes. So we put an entity, a relationship, another entity, and then the attributes are associated to the two components. This is different. We don't have a set standard. We can do a process to a process. We never have a relationship to a relationship or an entity to an entity. We always have to separate. An entity has a relationship with another entity. But processes can go to other processes, to other processes, to other processes. Data sinks can go to other data sinks, stores, they can go to another sink. Here's a data store going to a data store. Here's a data store going to a sink. You know, you can have any allowable combination of anything.
So it does not have to end with the terminator.
No, it doesn't. It can end with a sink. It can end, excuse me, that is a terminator. I meant to say store. It can end with a store. We don't have to end it with a terminator. We don't have to start it with a terminator either. So it's break time. That was lectures number 5 and number 6. We'll take, let's give it like 10 minutes. How's that? So get some water, some coffee or something, and then I think I'll talk about the midterm after the break. Break it up a little bit. Okay, so.